So in this session, we're going to look at improving web API security. So first, a legal disclaimer. And this is the agenda. First, we're going to look at HTTP 2. Then we're going to look at TLS 1.3. And then finally, we're going to look at mutual TLS. And we're going to take a couple examples of how to do that, one with Amazon Web Services and one with Azure. First, a little bit about me. I think most people probably know who I am by now, so I'm going to skip over this and the company I work for. So let's touch on actually HTTP 1.1 first. It's kind of the current standard. It was published in 1999 in Internet Age terms. That's dinosaur era. So it's, an overhaul of that standard has been long overdue, and as a result, HTTP 2 was presented in December 2014, proposed as a standard in February 2015, and it was published in May of 2015. So 7 years ago, over 7 years ago. So it's getting a little crusty as well, but we're going to talk about that with the next slide. It is supported by Chrome, Opera, Firefox, IE11, Safari, Silken Edge, in other words, just about every browser out there. It requires the use of TLS 1.2 or higher. This is the security piece. You can't use HTTP 2 and a lot of the older insecure SSL protocols. It just won't happen. And so that's the security piece. The issue right now is only 50% of websites support it, so it's still in the process of being adopted, even though it's 7+ years old. All the methods, status codes, and header fields are the same as 1.1. One of the big differences here, though, is that with HTTP 2, the data is transmitted back to the client in binary rather than text format. So not only is HTTP 2 more secure, it's actually significantly faster than HTTP 1.1. A number of other things that help increase the performance using HTTP 2 is that it allows the server to push data that the nodes of the client will need. That's not necessarily something that's important for a web API call, but when you're looking at HTML5 pages that may reference images, the server can push the images down to the client before the client asks for them, because it knows that it will need it because it's retrieving the page. It also allows for multiplexing of requests, so you can have several requests going on simultaneously. It allows for header compression, and then it allows the client to specify the prioritization of requests. So if the client makes 6 requests to the server for data, it can say, I want requests 2 and 5 to be done, to be given a higher priority than the other requests. I said I was going to touch on this. There is, because HTTP 2 is 7 years old, there actually is an HTTP 3 in the process. It was published in June of 2022. It's supported by Chrome and Opera, Firefox, Safari, though it's disabled by default, and Edge. So about 3/4 of the browsers out there support it. It requires the use of TLS 1.3 or higher, so it's even more secure than HTTP 2. The issue, though, is that only 6% of websites currently support it. So it is in the very early stages of adoption. So, maybe in a couple Elevate sessions a year or 2 years from now, maybe we're going to talk about it more. Right now, it's a little premature to talk about HTTP 3, at least being used by Parallel Labs. Part of the reason, perhaps, that the adoption is so low is because it is a more significant overhaul of the HTTP standard than 2 was. All the methods, status codes, header fields are the same, but they're coded differently and they maintain session state differently. And the data is transmitted over UDP rather than TCP. So some significant differences there. Okay, the way we implement HTTP2 is on the HTTP client, REST client, token request, and OAuth request objects. There is a new enable HTTP2 property. True or false defaults to false, but if set to true, then it will use HTTP2 for the request. And in addition, those methods that are used to attempt to make the connection, either HTTP 1.1 or 2.0, some new error codes have been added, or actually a new error code has been added to indicate that there was a problem establishing the HTTP2 connection. So if you make a request for HTTP2 and the server doesn't support it, then you will get this -20 error back, at least on the HTTP client send request method, letting you know that the server you contacted can't support the HTTP2. So for the demo, I'm going to use the Google Translate API, which does support HTTP2. And we'll do the demo here in a second, but I just wanted to show you it is more secure. That's kind of the focus of this session. But I also wanted to show the speed improvement. So for doing this this translate call using HTTP1, the transfer speed, bringing the data back, was 18 kilobytes per second. When I did it with HTTP2, the transfer speed was 88 kilobytes per second, so about 4 times faster on data transmission speed because of that binary format. So let's go ahead and take a look at the demo. Okay, so the first thing we're looking at here is using HTTP2. So I have a window here that uses the Google Translate service to translate text. And in the clicked event here, I check to see if the HTTP2 checkbox is checked. And if so, I enable turn on the property on the HTTP client that enables HTTP2. There is a property it's a function of the client now, which will tell me what HTTP version was actually used. And so I'm going to display that here at the end. Okay, so let's go ahead and run this. And in fact, I am going to run Charles in the background as well. And that way we can inspect the request to validate that it actually is using the version of the protocol that we want. And so I am going to do it first without checking the checkbox. And it says it used HTTP 1.1. We look at Charles, and in fact it used HTTP 1.1. I'm going to close the window and restart the app. So to make sure that we get a new connection, I'm going to say I want to use HTTP2. I hit the translate, and it says it used HTTP 2.0. We look at Charles, and in fact we did use HTTP 2.0. So that's HTTP 2.0. Okay, let's talk about TLS 1.3 now. TLS 1.2 was published in 2008, so it's also getting crusty. TLS 1.3 was published in August of 2018. In addition to being more secure than 1.2, that's the last point. It removes a number of options that are considered vulnerable now. Those are removed so that you cannot use those. But it's also faster. It has a faster handshake. It only requires 1 round trip rather than 2 to establish the connection. And it has a 0 round trip feature, which means if you've already established a secure connection with a site, when it revisits that site, it'll remember that it's visited before, and it will cut down on just in the initial establishment of the connection. Okay, one problem with this particular feature, because the Power Builder uses the Windows API call to implement it, the problem actually has to do with Microsoft Windows. There are only certain versions of Microsoft Windows that support TLS 1.3. That being Windows 11 and Windows Server 2022. Actually, Windows Server, yeah, those two, full support. With Windows 10 and Windows Server 2019, if you're on a specific build, namely 1903 or later, there is a way by modifying the registry to turn it on. Microsoft says that that is not for production use, though. And anything earlier than those particular builds of Windows 11 or Windows Server 2019, the feature's not available at all. So if you're still using Windows 7, this isn't going to work for you. Now, that's just because PowerBuilder goes to the Windows API. If you're on a Windows 10 machine and you're using Chrome, Chrome will use TLS 1.3, but that's because it doesn't rely on the Windows API to handle the crypto. It has its own libraries for doing that. So when you have clients that don't rely on the Windows API, like browsers or Java applications, they can do TLS 1.3 on Windows 10 and even earlier. PowerBuilder is limited because it's relying on the Windows API. This is the registry modifications you would need to make in order to explicitly support TLS 1.3 on Windows 10 or on, as long as you're on build 1903 or later, or on Windows Server 2019, once again 1903 or later. As I indicated earlier, Microsoft indicates that this is an experimental feature on those versions of Windows. It's not for production use. Frankly, even when I had these settings turned on, I tried to do I tried to hit a number of websites using TLS 1.3 from PowerBuilder, and it still didn't work. So you really need to look at migrating all your clients to Windows 11 if you're going to take advantage of the TLS 1.3 feature. Okay, the way that's enabled is there is a secure protocol. It's an existing property on the HTTP client. It's also on the REST client, the token request, and the OAuth request objects, which currently, or at least prior to this build, took the values 0 through 5. 0 is auto-selecting, where it starts at TLS 1.2 and then it works downwards to lesser and lesser protocols until it can actually establish a connection with the server. 1 through 5 indicate that a specific protocol will be used. 5, for instance, is TLS 1.2, and along those veins, then 6 means TLS 1.3, but it only will be TLS 1.3. It won't try to auto-select down from that point. So if you specify 6 and the client or the server doesn't support TLS 1.3, you'll just get an error message back. It won't try to negotiate downwards. And these are the error messages. This is once again for the HTTP client send request method, but the other methods have these additional error messages now. So if the client doesn't support TLS 1.3, you'll get a particular error message back, and if the server doesn't support it, then you'll get a different error message back. Once again, the Google Translate not only supports HTTPS 2, but also supports TLS 1.3, and that's what I'm going to use for my demo. Before I get to that, though, just to prove, unlike HTTP 2, there's actually a property on all these objects that will tell you what version of HTTP that you're currently using. And in the demo, you saw that where it came back and it said, I'm using HTTP 2.0 or I'm using HTTP 1.1. There's no such property on these objects to tell you what TLS or SSL TLS version you're using. So in order to demonstrate that the sample actually does use TLS 1.3, I did a Wireshark capture of the data. And you can see that the connection was established as TLS 1.3, and all the data was transmitted using TLS 1.3. So let's go ahead and look at that demo. So this is that same sample application that I used for HTTPS 2. We're going to call it Google Translate, which does support TLS 1.3. And so I just check that checkbox, hit translate, and we get results. Now, like I said, there's no property on the connection object that tells us whether what the protocol was. Because I selected 6, if TLS 1.3 couldn't be done, I would have gotten an error message back rather than data. So we know that it's using TLS 1.3, and as I showed you in the slides, I did do a Wireshark on it to actually validate that TLS 1.3 was used. Okay, now let's look at mutual TLS. So the first thing I want to do is compare what I would call here maybe normal TLS with mutual TLS to see what the difference is. So even when you're doing mutual TLS, you're still doing the normal TLS. So in the normal TLS, the client connects to the server sends down a certificate, the client confirms the certificate is valid, so it trusts the website or the API it's calling, and they start doing their data transfer. So it's a one-way authentication. The client validates the server is a valid server that it wants to connect to. With mutual TLS, the validation goes both ways. The client connects to the server sends down a certificate, the client confirms the certificate's in place, that it is valid. That's normal TLS so far. But at that point, with mutual TLS, now the client will pass a certificate up to the server, and the server will validate the certificate the client set. And then only if that certificate is valid for reaching that website or that API does the server actually grant access, and then they start communicating. So it's a two-way authentication. Not only does the client validate the server, but the server is going to validate the client. So that's where you get the greater security. You're going to create private certificates, issue them to the people who are allowed to use your API, and then validate in your service that the client that's attempting to connect is using one of those private certificates, and therefore it is actually authorized to use the API. Some differences here, particularly with regards to the certificate in normal TLS. The certificate issue, the server certificate is generated by a third-party trusted certificate authority. And when the client wants to authenticate it checks the validity of that server certificate chain up to the granting authority, which it knows about because it's got a list of trusted root authority providers. With mutual TLS, it's a private certificate that's used for the client. So the server operator generates a private root certificate. They create a server certificate based on that private root that the server is going to use to do the validation of the client certificates. Then the server operator issues a client certificate with a private key and password for each of the clients that is going to attempt to access this service, and supplies the client with that certificate. And then the client then uses that certificate in code to go ahead and authenticate back to the server. So for mutual TLS, I found a couple of popular API hosting sites that support mutual TLS: Amazon and Azure. Google. I looked at Google, and they have sort of a funky implementation. They still require OAuth tokens. What they suggest you do if you want to do mutual TLS is host a separate process in their environment. Do client certificate authentication to that. Have that go get an OAuth token for the use of their service, and then have that passed back to the client. So that really was not a real what I call a real mutual TLS implementation. So I'm going to limit the demos to Amazon and Azure, which have true mutual TLS approaches. Now, the way it's implemented in the client is through the set client certificate method that's been added to the HTTP client, REST client, token request, and OAuth request objects. So then that's where you would pass in the client certificate and the password, and then that certificate would be sent to the server once the server's been validated, so that the server can then validate the client. And like the other methods we talked about here, there are additional error codes now. These are for mutual TLS. So if you're attempting to contact a service that has mutual TLS enabled and you don't actually provide a certificate, you'll get the -16 error back saying you need to actually provide a certificate. If you do provide a certificate, but the certificate has no private key, you'll get the -17 error. And then if you provide the certificate, it has private key, but the password you supplied is incorrect, then you'll get the -18 error. So we're going to start with Amazon. We're going to see how we can do mutual TLS with Amazon. Well, the first thing you have to figure out is where in the Amazon cloud you're going to deploy your web servers. And it can be all the way down to a serverless environment like AWS Lambda, all the way up through basically a bare metal machine running in the cloud, and anywhere in between. For the purposes of the demo, I'm going to use Lambda. I'm actually just going to create a function within Lambda. I'm not going to use the .NET Core application there, although you can deploy .NET Core applications to Lambda. There is a Lambda library that you can include in your ASP.NET Core application, and what that does is it allows Lambda to actually act as a proxy the same way Kestrel does in front of the web service. So you can deploy .NET Core here as well as anywhere in between. But like I said, I'm just going to use I'm not going to use just a standard function within Lambda to do it for this demo. Once you've created your web service, you use the AWS API Gateway to configure an endpoint for your service. Now, the way that Amazon does this is when you've created your gateway, it gives you basically a subdomain within Amazon Web Services. It doesn't give you an IP address, and we'll get into that when we look at the differences between Amazon and Azure. So what I'm going to do with this subdomain within Amazon is I'm going to go into the AWS Routed 3 hosted zones, and I'm going to create a custom domain to use for the API. Because what I want to do is I want to have the first part of mutual TLS, which is the server certificate. In order to have a server certificate, I need to have a custom domain and create my certificate for the custom domain. So I will create the custom domain. I will use the certificate manager to create a public certificate for the domain. Remember, this is where we're using a third-party service, which is a trusted domain, a trusted root domain service to generate the service. I will return the AWS API Gateway, and I will associate the custom domain now with my API. I'll go back to the the Route 3 hosted zones, and I'll configure an A record for the custom domain to point to the alias for the API, that subdomain within the Amazon Web Service that they provided me. And at that point, that enables HTTPS. We've done the first half of mutual TLS. We haven't done full mutual TLS because all we've done so far is we've generated the server certificate. We haven't generated a client certificate and got the validation going yet. Now, one thing I pointed out here, what Amazon Web Services does is they give you a subdomain with Amazon Web Services. And I said you're going to create an A record. Well, this is something that Amazon allows you to do. If you use their registry and their domain services, is they allow you to point an A record to an alias. What they're really doing is they're creating what's called an A name record. This becomes a problem if you don't want to use Amazon. You can use your own domain registrar and your own DNS provider. If you do that, the first thing that's going to happen is Amazon's going to say, okay, you want to use this custom domain name that you got from some other provider, GoDaddy or HostGator or whatever, and you want to use it here. You need to prove that you actually own the service, and there's two ways you can do that. They will give you a CNAME record that they will expect you to put in your DNS settings, and you can do that. And they'll scan for they'll start scanning for it. And when they see that you've created that CNAME record, they'll say, okay, you're good to go. You can use this custom domain name for this API. The other option, which takes longer, is that you can have Amazon Web Services send an email to the contact information that's listed in the domain registration, and then have whoever that is that's listed for the domain respond back to that email saying it's okay for you to use the custom domain. And that can take a while, but you got to do one of those two things. The other issue you're going to have, though, is that your DNS provider must support the creation of an A name record, and you may not be familiar with an A name. An A name, the ones that people are familiar with really are the A records, and normally what an A record does is it points to an IP address. So you say www.mycompany.com points to this IP address. That's an A record, and a C name is where you point is where you use aliases. You can create aliases, but you can't use an alias for the root of the domain. What an A name record that's what happens when you get an A record and a C name record together and they have a baby, because that's where you can take a alias and you can point it to the root of the domain. So that's what Amazon is creating, basically, is an A name record. And you'll have to check with your DNS provider to figure out if they support the A name record. If they don't, you're not going to be able to use them to configure the custom domain for your service. Okay, that was an aside. Let's get back to doing mutual TLS now. Now, remember, for the mutual TLS, the client certificate is private. So we're going to go into the AWS Certificate Manager, but we're going to go to the Private Certificate Authority now, and we're going to create a private root certificate. Then we're going to create a private certificate for the server based on that root certificate. We're going to export that certificate in PEM format, and then we're going to upload it to an Amazon S3 bucket. And that's because now we need to go back to the gateway and tell it what the server certificate is going to be that's going to be used for the validation of the client certificate. So we go back into the AWS API gateway. We go into the custom domain for that API, and there's a checkbox that says Enable Mutual TLS. And the minute you check that, it's going to ask you for a trust store URI. And that's where you give it the URL to the Amazon S3 bucket. and that loads the certificate then that you just generated for the server, the private server certificate, up onto the API. And then the API will use that to validate the client certificate. What they also recommend you do, because if somebody gets a hold of that alias for your API, they'll be able to bypass mutual TLS, because the mutual TLS is associated with the custom domain name that you've mapped to the alias, not to the alias itself. So they recommend for security that you disable the default endpoint. I've actually left it enabled because I'm going to show you calling it directly. But once again, that's their recommendation, is to disable the default once you've got the custom working. Okay, we've got the server set up now to do the authentication. What we need to do now is get a private certificate for the client. So go back to the certificate manager. We create a private certificate for the client based on that same route that the server certificate was based on. We will export that in PEM format because that's the only option they give us. But then we can use OpenSSL to create the PFX format that PowerBuilder wants. And then the PowerBuilder application will use the PFX file to authenticate to the service. You actually saw the code for that a little earlier. So let's look at a demo of that. So here we're going to look at using mutual TLS with an Amazon Web Services deployed web service. In my sample application here, I've got a drop down where I can select which of the endpoints I want to call. So this is the one that Amazon originally provided me with, which is not through the custom domain. And then this is the call through the custom domain. I've got a use mutual TLS checkbox. And so if that is checked, then I attach the client certificate. Otherwise, clear the client certificate. And just to demonstrate that mutual TLS is actually working, I also have another certificate, which is not the valid client certificate for this service. And I'll go in here and change this. And see what happens when we send a certificate, but one that's not appropriate for the web service. And then go ahead and see if I get a response or an error message back. So let me show you something else first. Let's look at the Amazon Web Services console. I'm going to go into the API gateway. And so this is my service that I've exposed. This is, once again, the URL they gave me just when I exposed it, but not without the custom domain. But we have to have the custom domain in order to do mutual TLS. So we go to custom domains, and notice I've got mutual TLS turned on, and I've provided the URI to the S3 bucket where I've got my key that I created in the Amazon Certificate Manager. Okay, so let's go ahead and run this. And the first thing I'll do is I will call the default endpoint, and that will work even though I don't have mutual TLS checked, because like I mentioned, you have to use a custom domain in order to do mutual TLS, and that's why they recommend actually you disable that endpoint. Here's the one where I'm going to call it with mutual TLS. I'm going to attempt to call it first without a certificate at all, and I will get an error. I will say that I want to pass the certificate, and I get the response I want. And let me go back in here real quick and change the code so that it's going to send a certificate, but a bad one. And let's run that. And I will say mutual TLS, attempt to call service. Once again, an error message. I've sent a certificate, but it's not the one that's valid for the service. The only certificate it's going to accept is that first one I provided. And it works again. All right, so that is mutual TLS with Amazon Web Services. Okay, so now let's look at how we do mutual TLS with Azure. So the first thing you have to do, like you did with Amazon, is figure out, you got to deploy your ASP.NET Core code to Azure. One issue you're going to have here, though, is that at least when you're playing around with this, just as a sample, is that in order to support creating a custom domain, you need to be at least the B1 pricing tier. If you're going in, dev test, and you're just kind of playing around in Azure, normally you would use like an F1 or a D1 pricing plan. There's some other pricing plans too, but those are the three biggies within dev test. You can't do custom domains with those two lower price tiers. You have to be at the B1, or there's also pricing tiers within production and isolated. They're even more expensive. So you've got to be at B1 or higher to use a custom domain. Then you go into the Azure App Server domains and create a custom domain. You go into the app service. There's a custom domains option in the app service, and you associate the custom domain with the app service. In the app service TLS settings, you'll create a private key certificate for the custom domain. You'll create a binding between the custom domain and the certificate you just created. And at this point, you should be able to access the API versus via HTTPS. This is the server piece. This is where we're creating a server certificate. We haven't implemented mutual TLS yet. Okay. Here's where you may have some some issues, like but different than we did with Amazon. With Amazon, the problem with the custom domains was that you needed to have a DNS provider that supported A names in order to use a third party. We have kind of the opposite issue with Azure. If you're going to create a custom domain in the app service in Azure, they require that you have been with them with a billing history of 6 months or more. If not, you're not allowed to use their domain services. So this is where you may be forced to use a third-party domain provider. Fortunately, this is where Azure differs from Amazon. When you create your API, they give you an IP address. So you can create an A record. You don't have to go through this A name record business that you do have to do with Amazon. So one thing you'll have to do, though, since you're going with third parties, you need to prove to Azure that you own the service. That you own the custom domain. So what they'll do is you can actually do two approaches. You can either create an A name and just go ahead and map it directly to the IP record, or you can create a C name record with according to the values that they provide to you, and then they will know, yeah, you own that custom domain, you're valid. Now you can go back to the app service, custom domains, and you can associate the custom domain with the API. Once again, at this point, we're still just doing HTTPS. We aren't doing mutual TLS yet. So let's do mutual TLS. So go into your app service, go into configuration, general settings. There is an incoming client certificates option, and that's usually set to optional or ignore. We need to change that to require. And what that says now is that the service will require the client to send a certificate. We're not validating the certificate at this point. We're just requiring that one be sent. So if the client doesn't send a certificate at all, it can't connect. Now it can send a certificate but Azure is not doing the authentication. Also, as a side note here, in the incoming client certificates, you can also set up exclusion paths. So if you want certain clients to be able to connect using mutual TLS and certain clients not, you can actually enable that in Azure. But let's get to the authentication piece, because that's where Azure gets a little more complicated than Amazon. Amazon, you put the server certificate on the server, you create this client certificate, you have the client send the certificate, and Amazon just goes ahead and does the validation for you. In Azure, you have to do it yourself. What Azure will do is when it gets the client certificate, it will forward it to your API, but it leaves it as the responsibility for your API to do the authentication. So this is how we're going to do that. We're going to go into our setup CS file for our service. And the first thing we're going to do is enable forwarding options so that we can receive the forwarded headers, including the client certificate, into our service. And this is also in the startup CS file. This is where we add the certificate forwarding and add the authentication. And we're going to create a separate class that goes ahead and does the authentication for us. And then we validate the certificate. And then if it fails, we'll say, the certificate that was sent in wasn't valid. Otherwise, it continues on and the service goes ahead and works. We need to put this in the startup CS file as well. Once again, we need to allow the forwarding of headers and the certificate forwarding, and use the authentication and HTTPS redirect. So this is the authentication class that I created that we then use for the client authentication. I've done a really simple example here. In reality, you would want to hopefully do a bit more work in order to determine the certificate's valid. Check the date range, and maybe the root certificate that was used to generate the certificate, all that kind of stuff. All I've done is I figured out what the thumbprint was for the client certificate I generated, and then I'm going to read the certificate that was sent in from the client and make sure that the thumbprint matches the thumbprint that I generated. Okay, let's take a look at a demo of that. So now we're going to look at using mutual TLS with Azure, and same sample application. The only thing that's going to change is the service call I make. Let's go ahead and look at the Azure console though. So I go to my app services, go down here into the configuration, and general settings, and scroll down here, and you notice that the big change I make here is normally this is set to allow optional. We're going to turn that on to required, so we can't call this service without sending some client certificate. But remember, and here's the exclusion path in case you want to provide access without requiring a certificate. But remember, the validation of the certificate is done in your code, not by Azure, which is the different between Azure and Amazon Web Services, where Amazon Web Services does the authentication of the certificate. So anyway, that's the console. Let's go back to our application and run this. And this time we will call the Azure service. I'm going to try it out first without a certificate, and I get an error message. I will try it with the certificate. Okay. Took a little while, but there it was. And then let's go back and do the same thing we did with Amazon. I am going to send some other certificate, not the certificate that's actually required to run the service. And once again, it fails. It'll only work if we call it using the certificate that we've created to allow to authenticate the client to the service. Okay, so that's mutual TLS with Azure. And that's it. Time for questions and answers. Bye.